All right, here we go with our classwork on standard deviation. So we're going to start with looking at an example that has to do with two different cities and use that example to sort of break down the formula into all the different steps and why we're doing what we're doing. So really figuring out how does this standard deviation thing work and seeing kind of an example of it as we work through it. Then we're going to wrap up with some questions that are designed to get you thinking critically about standard deviation. But before we get started on that, a little quick review from last time. So what are the three ways of characterizing a distribution? So this is maybe stated a little differently than you expected, but um, as we said last time, we really look at three things to describe or characterize our distribution. So those three things that we first look at are, of course, shape. And we discussed shape when we were looking at, excuse me, when we went over dot plots and histograms, right? So what is the general shape of our distribution? Then last time we looked at center and we talked about the mean and why it's so meaningful and why we tend to use it a lot more often than we do the median. Now today we're going to be talking about this last way, spread. So this is another thing that when we first look at our data and we visually assess it, or if we want to just have kind of a snapshot of what is this distribution like, we would want to say, okay, well, the shape is roughly this, the center is around here, and we want to give a measure of, okay, and how spread out are all the data points? Are they really, really tight together or are they really spread far apart? Because that makes a difference too. And just especially if all we know is the center, well, how close are all the other data points to that center? Right? We don't know that with just these two things. So we like to talk about spread as well. How spread out is it? Are all those data points really, really close or are they all pretty far apart from each other? What kind of variability do we see in our data set? So this is what we're going to be talking about today um, to help us, again, just give sort of a snapshot of what does my data set look like, or, what is this data set like? Okay, summarizing spread with standard deviation. So look at these two distributions of temperatures below. The table, which we see here, and the dot plots here show you the same distributions, one distribution for St. Louis and one for San Francisco, but in two different ways. So we can see in this table, we are viewing monthly normal temperatures in Fahrenheit for St. Louis and San Francisco. So in the top of our table, we have which month, right? So there should be 12 of these, January through December. And then the top data line of our table shows those monthly normal temperatures for each month, right? For St. Louis. So we can see in St. Louis in January, the normal temperature is about 29. In February, the average normal temperature is 34. If we come out to July to see how their summer temperatures look, we would see that the average normal temperature in July for St. Louis is 80. Okay, so that top line of data is telling us the average temperature for each month in St. Louis. The next line down in our table, we're looking at the monthly normal temperatures for San Francisco. Okay, so we can see in San Francisco in January, monthly normal temperature 51, in February 52, in March 55, April 56, right? So we can see those values for San Francisco in that bottom line. And again, we have 12 data points, one for each month for each of these two cities. Now we see the same information that's presented in the table here in the dot plots here. Again, St. Louis is on the top, San Francisco is on the bottom. And we can see this is displaying it as dot plots. So we have our range of temperatures from 30 up to 80. And we can see the dots correspond to the data points. So there's one up here at 29 for St. Louis, and I can see that's the one for January. And so by scanning across, I can see those monthly normal temperatures graphed out across this number line. If I look at San Francisco, I can see those values right in here, right? They're all within this kind of area. So on number one, I want you to consider by looking at the dot plot only, so I don't want you to calculate anything, right? So no calculators, no numbers, just by looking at the dot plot. I want you to kind of eyeball it and try to find one single temperature value that you think best represents all of those normal temperatures. All right, so do this first for St. Louis. So just by eyeballing, and remember, keep in mind that idea of the mean and balance. So if you're looking at all those pretty spread out data points for St. Louis, if you had to pick one spot, one value, one temperature value, then what would you pick as sort of that best representative of the entire year for St. Louis? Okay, so pick a temperature that represents sort of the whole year in St. Louis, and then do the same thing for San Francisco. So eyeballing it, looking at that data, thinking about, what temperature would best represent these values that I have for San Francisco. So take a moment and do that. Pick one for St. Louis, one for San Francisco. And then once you have your two values, I want you to look at them and consider how do they compare to each other? Are they close? Are they far? How are they? Okay. Now we'll consider a couple of questions that put this data into context to really help us think about what do these numbers mean, right? So on number two, suppose you have a friend who's going to move to San Francisco. The only piece of information that your friend has about the weather in San Francisco, because apparently they don't have access to the internet, is that the mean temperature is 57 degrees. That's all your friend knows. The mean temperature in San Francisco is 57 degrees for the year. Will your friend be able to pack clothes that are appropriate for the weather? So, keeping in mind the data we have, if all they know is the average temperature is 57, will they be able to pack appropriately? And then why or why not? On number three, I want you to consider, similarly, what if your friend was going to move to St. Louis in January, and all she knows is that the mean temperature for the year is 56 degrees? Will your friend be able to pack clothes that are appropriate for the weather? And again, why or why not? Looking back at this data for St. Louis, right? If all they know is the average temperature in St. Louis is 56, how are they going to do? And then think about your answers to questions 2 and 3, right? So think about the friend moving to San Francisco, the friend moving to St. Louis. And I want you to think, what do they tell you about the representative temperatures for those two cities? So basically, what do they tell you about how well those average temperatures of 56 and 57, how well do they fit the temperatures for that city for the year, right? How well are they at, or how good are they at representing the temperatures? Once you've considered that, I want you to go back to the dot plots and take a look again at the data for both St. Louis and San Francisco, and then write a sentence comparing how variable the monthly normal temperatures are for the two cities. So remember that term variable in this context, um, it really means how spread out or how much do they vary or differ, right? So looking back at the data, at the dot plots, consider which city seems more variable, more spread out with more differences in values, right? So compare the two cities with regards to how variable they are and try to come up with a sentence to do that. Okay, now one measure of variability that we look at for individual data values, right? Not a whole set, but just an individual data value if you want to know about the variability of that data value. One way that we measure that is looking at the deviation from the mean. So when something deviates from something else, that means it's different from that thing, right? If you think about a deviant or something, deviated septum, that word means it's different from whatever, right? It's deviated from something. So in this case, we look at deviation from the mean. How far does that individual data point deviate from the mean? How far away from the mean is it? Right? Is it really, really close to the mean? Or is it very far away from the mean? How much does it deviate? So the deviation from the mean, again, how much does one data value deviate or differ from the mean of the data set, right? If we know the mean of the whole data set, where does this 1 point fall? We can talk about that deviation. So to calculate the deviation, it's pretty straightforward. The deviation is just we take that data value, whatever value we're talking about at that moment, and then we subtract the mean of the data set. So this is essentially saying like, okay, we've got some point, and we want to figure out how far away from the mean it is. So the mean might be above it. And so if we take this point and we subtract whatever this mean value is, then we're going to get a negative deviation. And that's because our point is deviating to the negative side. It's less than the mean. Now, if the mean is actually below our point, let's say the mean is somewhere over here, then we want to know how much deviation is this? How much spread do we see between the mean and that data point? Again, we would take our data point, subtract the mean, and that gives us sort of that distance, right? So let me just draw this a little bit bigger because that's really what we're talking about here is we're talking about distance from the mean, right? So wherever our mean is, I'm just going to use a, I don't know how, I don't know why I'm doing dots, but let's just say we have like whatever the mean is, okay? And I'm going to put the little mean symbol there. Now I could have a data point that's below the mean. And so when we talk about the deviation, we're talking about this distance. How far below the mean is it? Or we could have a data point that's above the mean. Let's make one that's, close, but above. So then we would be talking about that little distance there. How much does that data point deviate from this mean? And so whether we get a plus or a minus tells us if it's above the mean, then we're going to have a positive deviation because the data value is bigger than the mean. If we end up with a negative value, that's because our data value is lower than the mean, and so a negative value tells us it's below, whereas a positive one tells us it's above the mean. All right, so this deviation tells us two things. Is this point above or below the mean? And then how far? Is it really close or is it far away? So here in these two tables, they've been split up now, St. Louis and San Francisco. We have the mean for almost, because there's one missing, as we'll see, every month in St. Louis and San Francisco. So I want you to fill in the deviation from the mean for St. Louis's January temperature. Okay, so if you understand this concept so far and you want to go ahead and pause your video and try to find out what is the deviation for St. Louis, Otherwise, here I'll give you another small example to kind of help you on your way, give you a chance to try it out. So let's say we have a data set that has a mean of 46. And then I have one data point in that data set so a data value of, let's say my x would be, in this case, 58. So if I wanted to figure out the deviation of this data point from the mean of the set, then what I would do is take my x and subtract the mean, right? That's our formula here. So what is my x? My x is 58. Then minus the mean. The mean is 46. And I would get 12. All right, so a data value of 58 has a deviation from the mean of 12. So this means that 58 is 12 above the mean. Okay. If, let's say I'm looking at a different value, I'm just going to label it x2 so we know it's different. Let's say I had a data value of 24. Okay. Well, 24 minus 46 is negative 22. So that tells me that this data point is 22 below the mean. This one was 12 above, this one's 22 below. And finally, let's say that I have another one that's 46. I have an actual data value of 46 in this set. Well, the deviation between 46 and 46 is nothing, right? Because in that case, if we're imagining that mean of 46, right? 58 is way above, 24 is way below. Where does 46 fall? It's right on top of it. If it's right on top of it, then there's no distance between them. There's zero distance. Okay? So hopefully that helps you kind of figure this out. So just take a moment and calculate, given that temperature for January, and remembering that, the mean for St. Louis, as a reminder, is for the whole year, it's 56. And the mean for San Francisco for the whole year is 57. Because you're going to want to have those values in order to calculate, or at least this value, in order to calculate that. Okay, so that's all well and good for one data point in our data set, right? If we want to talk about variability for an individual data point, then we can talk about how much it deviates from the mean. But what we really want, because we're not usually talking about individual data points per se, we were really talking about, data sets is what we talk about a lot. So how do we figure out how much that whole data set varies, right? Not just one point, but like if I had a way to summarize, how much variability do I see in this whole data set, right? All these different pieces of data. Well, one approach to measuring variability is to calculate the average deviation, right? So I want you to, let's think about San Francisco here. So we have the monthly temperatures, and then we have how much those temperatures deviate from the mean in this bottom row, right? We can see it looks like it spans from about -6 to +6, okay? But some months are really, really close to that mean, where some months are further away. So how do we represent all of this variability that we see as just like one number, one way to say this data set varies about this much, right? That would be really convenient if we had something like that. Well, we could try to calculate what's called the average deviation. So I want you to think, so basically find the average of all of these deviations, right? If we want some way to summarize them, well, let's just find the average. And then we could say, well, on average, the data points differ from the mean by about blah, 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 right? So I want you to take a moment, pause the video, get out your calculator for this one, and I want you to compute the average deviation for both St. Louis, either one, honestly. So you can try for St. Louis, you can try for San Francisco. If you really want to practice, try both of them. But in other words, pick one of them, and then I want you to calculate the mean for these deviation values. All right, so how do we calculate that mean? We're going to add them all up and then divide by 12, right? 12 months to the year. So go ahead and pause, choose your city, and calculate the average deviation so we can figure out, okay, on average, how much do these points deviate from the mean? Okay, so hopefully you had a chance to do that. Just a little advice also for any calculations you do, whether by hand or by calculator. I always recommend that you do the calculation until you receive the same answer twice in a row, just because it's very easy to make small mistakes. And if you only do it once, um, you could have made a mistake and you won't know. So always double check your work. And I recommend, like I said, do it until you get the same answer twice. And then I feel pretty good about it. So this is maybe a bit of a trick question. I don't like trick questions. I don't like to use that terminology, but um, hopefully you found that regardless of which city you chose, St. Louis or San Francisco, the average deviation is 0. Right? So the sum of the deviations, if you add them all up, then you should have gotten 0, whether you added up these deviations or these ones. Right? So this isn't really a trick. It's true for every data set. The sum of all of the deviations is always going to be 0. Why? Well, because of what we talked about last time. Because the mean is the point where all the deviations balance out on both sides. So remember the 5, 5, 5, 10, and 20 from last time? So if you think about it, let me pull up another sheet here. Okay, so if we have, this is representing the mean on our number line. In this case, we'll go with that example again, where we had 5, 5, and 5, each with being 4 below. And then we had 10, which is 1 above, and then 20, which is 11 above. The cool thing that the mean does is it balances the deviations, right? So when we added these up, we get negative 12 on one side. If we add these up, we get 12 on the other. What happens if you add together 12 and negative 12? It's always going to be 0. So this is because that's the mean's job. The mean's job is balance all of the deviations. Well, if the deviations are always going to be in perfect balance around that mean, then when you add them all up, you're always going to get 0. So, okay, so maybe the average deviation isn't the way to go, right? Because, shh, sorry, because for any data set, the average deviation, if it's 0, then how does that help us to summarize a variability? Every data set's going to be the same and it's all going to be 0. So that doesn't really help us, right? Now, think about it intuitively. For those two cities, St. Louis and San Francisco, intuitively, like which one do you think should have a bigger average deviation, right? If it didn't come to zero, how much do you think, if it's very has a lot of variability, then it should be bigger, right? That average deviation. Versus if it has very little variability, then we would expect it to be smaller. So between St. Louis and San Francisco, which one would you sort of intuitively expect should be bigger? Now, there are a couple things that we could do to keep the deviations from canceling each other out and always adding up to zero. So, one, we could get the absolute value first and then average them, right? So just instead of having any negatives, we turn all the negatives into positive, add them up, and then find the average of that. Okay, so that's way one. I'm going to tell you, we're not going to do that way. We're going to do way two. You may think, why? Just because it's harder? So, way two, we're going to square all of the deviations and then square root them later, right? Because if we're squaring, we're making it really big. We want to bring it back down to kind of the same unit of measurement by squaring it later. So, the reason why we pursue this second method is for algebraic reasons. And honestly, it has something to do with, it's like, if you think way back to high school math, not to traumatize anybody, but if you think back to like Pythagorean theorem, where a squared plus b squared equals c squared, but if it's just a plus b, it doesn't always equal c, right? That it doesn't work unless it's squared. It's something like that. It's like the algebra theory behind it, that if we just do the absolute value, then when we do other stats calculations that involve the standard deviation, then it throws the calculations off. And I've never really been interested enough to look into why. If this is something that is going to be a burning question for you, I encourage you to explore. But for whatever reason, it doesn't end up working out well if we just use the absolute value. So it's not just me saying, let's make this harder to make it harder. It does have a reason that ties in with like more advanced statistical theory about why we do the square and square root thing. Okay. So you can take my word for that, or you can look it up to you. Now here is the same table that we had before for St. Louis, but now it has another row added to it. So we have the month, the monthly normal temperature, the deviation for that month from the mean, and then we have this new row where the deviations are squared. So when I say squared, just quick review, right? I mean you take that number and you multiply it by itself. So if you take negative 27 and you square it, what you're doing is doing negative 27 times negative 27. And so let's do that, and we get 729. That's where this squared deviation comes from, right? And I could also do it this way if I did 27 negative, and then I just hit that square button. Same thing. So 22 negative squared, 484. 11 negative squared, 121. 1 squared, 1. Right? 10 squared, 100. So we can see this bottom row, we're just squaring all of the numbers above. So I want you to take a moment and, just for practice, calculate for December, what is the squared deviation for December? Okay, and again, remember that. So, I mean, we don't even need any other information here, right? Just want to square that and put that in. So now if you add up all of our squared deviations, so if we take this bottom row and we add them all together by totaling all those values in the bottom row, then the sum is 3640. And if you want, you can pull out your calculator and you can double check this by adding 729 plus 484 plus 121 plus 1 plus and so on. But I'm just going to let you know I've done this several times, and it adds up to 3640. Okay. Now, this number has its own special little name. It is called the sum of squares. Shh. Or you'll see it often abbreviated as SS. So why is it called the sum of squares? Well, because we squared all the deviations and then we sum them up. We add them all up. It is the sum of squares. Okay, so that's where that term comes from. Now, if we were to divide that number, that sum of squares, if we were to divide it by n, quick review, n means the number of things in our set, right? So in this case, our n is going to be 12 since we have 12 months. So if we took that sum of squares that we add up all the square deviations and then divide by the number that we just added up, we would get the average squared deviation, right? So this is basically the average of all those square deviations, right? We add them up and divide by however many we added up. Okay. Now this number also gets a special name in statistics, and this is called the variance. The variance is essentially the average squared deviation. Okay. Just to kind of connect with some terminology. Now, the variance is an important way of summarizing how spread out a distribution is. The sample variance, right, so just to add a couple of notes here. So we've got the sample variance is, we denote that, or what we use to refer to that is this symbol, S squared. Now, it's important to know that there is the sample variance, what we've got here, which is calculated based only on a sample of data. But we also can calculate, or we can have the population variance. And this is where it starts getting back to all those symbols and the difference between the symbols, right? So the population variance, we use sigma squared to represent the population variance. Now, the population variance can only be calculated if we have data for the entire population, which usually is not the case. Now, the reason this is important is that the formulas for these two things, these two variances, they're slightly different. Okay, and I'm going to go on a little tangent here, a little mini lecture, if you will, to go over why these two formulas are actually a little bit different, right? So what we've got here, let's see. And this is, by the way, this is a very difficult concept. So if you don't follow, if you get lost, totally expect it. That's very normal. It's a tough concept. I'm going to do my best to try to explain it to you, but at the end of the day, in application, it's not going to be that much of a it's not something we really need to worry about a whole bunch, but just to kind of give you the background here. Okay, so again, just so we have all our information, so we've got our sample variance, which is S squared, and then we have the population variance, which is little sigma squared. Okay. So why are there different formulas for the sample variance and population variance? Now, keep in mind that the sample is drawn from the population, right? So we've got the population is always going to be bigger than our sample. Our sample comes from this population, but it's smaller, right? Because it's not everybody, it's just selected values, right, that end up in our sample. So when you think about it that way, the population, since it's so much bigger, that means there's probably at least a little bit more variance in the population than there is in the sample, right? Because we have more people, more data, more differences, right? Which do you think we're likely to see more differences in? A group of 1 million or a group of 100? Right? I would put my money on 1 million that probably because there's 1 million, there's just so much more. There's probably more differences in that bigger group than in the smaller group. Now, what this means for us is that the population is always going to have a little bit more variance than our sample. And some hardworking statisticians, right, from I don't know when, because this is not a history of statistics class, but somewhere along the line, there were some fabulous statisticians who figured out that this is more important, this difference of more variance and less variance. This makes a bigger difference. This is a bigger deal when we have a small sample, and it's less of a big deal when we have a really large sample, right? So again, if we had two samples and one was pretty small and one was, quite a bit bigger, then again, the bigger one's probably going to have more variance. So the difference that we see between bigger samples in the population, it's not going to be as big of a deal as we see between small samples in the population, right? So if we're trying to estimate, consider that when we're using a sample and we calculate a sample standard deviation, what we're doing is we're trying to explain, or if we calculate the sample variance, we're trying to estimate for the whole population, right? That's who we really care about. We can say this is what it is for the sample, but really what we want is like, what do we think it is for the whole population? So, which do we think is going to be a better estimate of a whole population? A little sample or a big sample? Chances are that the bigger the sample is, the closer that sample's variance will be to the true variance of the whole population, right? If this gets bigger and bigger and bigger, the closer you get to the size of the population, probably the closer those two are really going to be. So, how does this connect to the formula? For this, let me just kind of clean up a bit here. Okay, so how does this connect to our formula? And just for kind of reference, we'll have big pop, little sample, and let's say a bigger sample, just to kind of illustrate what we talked about. So for the population variance, to get this sigma squared, we do what we just did in the temperature example. So going back here, what we did here, where if you add these all up and you get 3640 is the sum of squares. And then if we do, okay, well, what's the variance? 3640 divided by 12, then that would give us the variance. But this 12, this n, is only for the population equation. So here, we're really just working with a sample. This isn't the whole population of all of the temperatures of the city, right? So we're looking at a sample, so we really wouldn't use this 12 in this case. But if this was the whole population, this is exactly what we would do. We would get that average squared deviation, and that is the variance of the population, right? So we would take, so the population one, where we have population variance, for that one, we really are doing the sum of squares, where you find the deviations, you square the deviations, you add all the squared deviations up to get that number, and you divide by how many are in your population, the population size, right? So this is the accurate formula for population variance. Now, we know, based on our little conversation, that the population variance is always probably going to be at least a little bit bigger than our sample variance. So what we do is we adjust the sample equation a little bit to kind of adjust for that difference, that we know it's always going to be a little bit smaller. So if we're wanting to estimate for the whole population, if I know my sample value is going to be a little bit too small, what can I do to make it a better estimation? Well, I can make it just a little bit bigger. And so that's why we have two different formulas. So for the sample variance, we divide by a slightly smaller number, which gives us overall a slightly bigger result, right? So for the sample variance, we take that sum of squares and we don't divide by n, we divide by n minus 1. N minus 1 is going to be a little bit smaller than n. And when we divide by something a little bit smaller, it's going to make the overall thing a little bit bigger. All right, so here's our second formula. So let's, just to kind of illustrate that example, let's say we divide, oops, my hands are touching things. So if we divide a slightly smaller number, divide by a slightly smaller number, the overall result is slightly bigger. So if you think about what's bigger, 3 divided by 4 or 3 divided by 5. All right, so if we have 3/4 versus 3/5, which one is a little bit bigger? This one, right? So so the effect of this change, right, of going from n, going from 5 to n minus 1, 5 minus 1 is 4, the effect of subtracting 1 from the bottom means that this guy's just a little bit bigger. And that's what we want if we're trying to estimate for the whole population. We'll say, okay, I get this value from my sample, but it's probably a little bit too small. So let me divide by 1 less than n. And it makes it a little bit bigger, and that's going to be a better estimate for this whole population. Now, when do we think this matters more? Well, let's say if I had a sample size of 10, then the difference between something over 10 versus something over 9, let's say, like, I don't know, just pick a number. 8 out of 10 versus 8 8 out of 9. That difference is going to be a lot bigger than 8 out of 10,000 versus 8 out of 9,999, right? There's still only a difference of -1 between these. But when the numbers are smaller, when your sample is smaller, it's going to have a bigger effect than if we're using really big sample numbers. If we have a really big sample, the difference between 8 divided by 10,000, 0.0008, and 8 divided by 9,999, again, it's going to be 0.0080080, right? So it's a tiny, tiny little difference versus 8 divided by 10 and 8 divided by 9. That's a much bigger difference. Okay, so when we're dealing with large samples, this n-1 doesn't change things a whole lot. But when we're working with little samples, it does have, it does bump up that that variance to help be a better measure, better estimate of that population variance. So again, super hard concept. It's really a hard concept to explain. So if you followed any of that, good. Good for you and good for me. If you didn't follow, if you got lost, that's okay too. It's tough. Really, what we want to remember is that when we're working with samples, which is most of the time, we don't divide by n on the bottom here. We actually divide by n-1, and that's to accommodate for differences between a sample and estimating for the population. And I'll go ahead and I'll link to another video of somebody else explaining this concept. Maybe he explains it a little differently or a little better than I do. So if you want to see it told a different way, then you go check out the AP Stats Guy video. But really, what's important here is that we have these two formulas. We have one for the population variance and one for the sample variance. All right, clean up a little bit here. And the difference between them is that the population one is divided by n, and the sample one is divided by n-1. Now, this is so that the sample variance becomes a little bit bigger to make up for the fact that the variance we see in the sample is generally smaller than what we really expect for the population. And that's always what we're really trying to estimate for. Right? We really care about the whole population. Okay. So back to this classwork. Now that we took our detour, let me just add these in here so we have them together. So the variance is an important way of summarizing how spread out a distribution is. The sample variance is denoted by S squared. Population variance is denoted by sigma squared. Why should we be using this version here? Well, because these 12 temperatures, that's just a sample. That's not a whole population, right? So because we're dealing with a sample. And in our sample, we have a sample size of 12, right? 12 data points for our sample. Okay. So since we are calculating S squared, since it's a sample, we divide the number from number 10, all right, this one that I gave us, 3640, sum of squares. So just so we have all this together again, that's the sum of squares divided by n-1. We have from number 10, 3640. Let me double check that just to make sure. Yes, 3640. And our n equals 12 for the 12 months. So we can plug these in, right? And actually, we're going to do that in the next step below. So here we divide the number from number 10 by n minus 1, not by n. Why? Because we're working with a sample. What does this do? It makes this estimate just a little bit bigger to be a better estimate of the population variance. Okay, so here we've got a repeat of our formula for the sample variance. Note that n represents the sample size, the number of data points in our distribution, which in this example is equal to 12 for each city. So here we're going to calculate the sample variance for St. Louis versus for San Francisco. And look how nice I am. I don't even make you do this yourself. We plug in our SS over n minus 1, and I get the sample variance for St. Louis is 330.91. Okay? And if we do the same thing for San Francisco, if we plug in, if we found our sum of squares and then divided by n minus 1, we get this sample variance for San Francisco is 13.64. Now, we're still one step short of where we want to be. So keep in mind, here, these are all squared deviations, right? So we've taken those temperatures, those deviation temperatures, and we've squared them. So really we're talking about like degrees in Fahrenheit squared in this step, right? Degrees squared. So if I tell you the variance for St. Louis is 330.91 squared degrees, how helpful is that in informing you how to pack for, to pack for the weather for St. Louis? It's not very helpful because what the heck, 330 squared degrees? Well, like what is that in real money, right? So since we've squared all the degrees, we need to undo that. Okay. So the variance is an average of the squared deviations, but squared deviations are not really what we're interested in. It's not our initial unit of measurement. So what can we do to turn it into an average of the deviations? So if we squared everything, what do we do to undo squaring? That's where our buddy, the square root function, comes in. Okay, so we're going to take the square root of each of these to undo that squaring that we did. So when we take the square root of the variance, then it's called the standard deviation. And it's denoted by S, right? Because if we take the square root of S squared, we get S. So we can calculate the standard deviation for the temperature in St. Louis and San Francisco, right? So for St. Louis, if we want the standard deviation, that's in just regular degrees, then to do that, we wanted to take the square root of the variance. Um, let's see. Oh, it's right there. Okay, so 330.91, take the square root, 18.19. Okay, 18 degrees makes a lot more sense to me when we're talking about the weather than 330 squared degrees. Agreed? Now, we can do the same thing for San Francisco, but this time we're going to use San Francisco's variance. So we can do 13.64, take the square root, and we get 3.69, right? And so this is degrees Fahrenheit, now that we've undone the square. So I'd like you to think about these values, right? And I want you to consider, like, how could we write a sentence interpreting the variability of monthly average temperatures in St. Louis and San Francisco using these standard deviations for each city? All right, so I'm going to go, you can go ahead and pause and try to write your own sentence, and then I'm going to write my sentence here. Okay, so I would say, and again, yours can be different than mine. This is just how you write it up. But this is how I would interpret it. So the monthly temperatures of St. Louis vary on average by about 18, yeah, just leave it where it is, by 18.19 or 18.2 if you want to round, about 18 degrees from the mean. All right, so in St. Louis, those average temperatures, they vary on average by about 18 degrees from that mean of 56. Versus in San Francisco, temperatures only vary by about 3.69 or 3 degrees from the mean. Right? It's important to remember that we're talking about from the mean or around the mean, and really we're kind of saying like on average. On average, what kind of deviations do we see? Well, in St. Louis, we see deviations on average about 18 degrees, versus in San Francisco, we see them on average by about 3 to 4 degrees. So does this kind of make sense? Right? So taking a look at these deviations for each city again. So we're saying that for St. Louis, using our roundabout square and unsquare method, these temperatures vary about 18 degrees from the mean of 56. Right? Some are a lot lower, some are really close to 56. But if we were to kind of average out how much do these points vary from the mean, we would say like about 18 degrees. Right? That's about how much spread we see on average. For San Francisco, we see remember the deviations are a lot more clustered together. They're really close together. And here the mean was 57. So in San Francisco, these deviations, if we were to kind of average these out, some are really close, some are a little further. But if we were to average them out, on average, they vary about 3.5 degrees. Right? Does that make, so do these numbers kind of make sense here? 18 as the average of these values and 3 point something as the average of these values. So do the two standard deviations seem like reasonable average deviations from the mean? Now, these last few questions, I'm going to have you really think about, and I encourage you to use the discussion board, or if you have like a partner in the class or a study group, these are good questions for talking over with each other. Just so everyone's on the same page, let's go ahead and put our 18 that we got in there. So, thinking critically about standard deviation. Let's think about what standard deviation tells us about the distribution, right? The concept. What is it? What is it telling us if we were to see the standard deviation is 8.3? What is that telling me? So, we can think of it as standard deviation is kind of roughly an average of the deviations from the mean, right? If we have some data set and we've got our mean, there's going to be points below it, there's going to be points above it. We want to know, are the points really close to the mean or are they spread far apart? Right? So this standard deviation is giving us a way to sort of summarize that. On average, our data points are about this far away from the mean. Okay? So in some sense, the standard deviation gives us the average distance of the data values from the sample mean, right? We're saying like how far are they away? What's the average distance from the mean? So if you think about the standard deviation for St. Louis, which is 18, or if you want to be more precise, 18.19 degrees Fahrenheit, what is the interpretation of that number? Right? So what does that really mean? And then here, I want you to think about, could the standard deviation of a data set ever be negative? So thinking about the concept of standard deviation, you can think about how we get the standard deviation. What does it stand for? How do we get it? Can it ever be a negative? Right? And think about why or why not. Again, these are really good questions to talk over with somebody. Then, could the standard deviation ever be 0? Is it possible to have a data set with a standard deviation of 0? And if so, what would that look like? How do you get that? What does that 0 mean? Right? And then lastly, I want you to really think about, how are the concepts of mean and standard deviation similar to each other, right? And so here, I'm going to give you a little bit of help here, but right when we're talking about the mean, we're talking about what's the average value. When we're talking about the standard deviation, we're kind of talking about, well, what's the average distance from the mean? Right? So in what ways could we consider those similar? And then how are they different? Because they are measuring two different things, right? So what are the two different things that they're measuring? How are they similar? How are they different? So some questions to encourage you to just think about this concept a little more. Make sure, thinking about what does it mean, to try to wrap your head around it. And then finally, just as an extra little bit, I'm going to go ahead and summarize the steps. And this is just extra. And you will not have to calculate the standard deviation by hand in this class, but I can't guarantee you won't have to in any other classes. So just to kind of summarize what we did, well, the first step, take your data set and we need to know, what is the mean? If we don't know what the mean is, we can't figure out any of the deviations. Then we want to subtract. So we want to do for each data point, we want to subtract the mean, right? To get our individual deviations. So for every number in your data set, take that number and subtract the mean and record the deviation. Then we want to square those values. Square the deviations we get. Next, add up all of our squared deviations. Add up everything from step 3. And this gives us our sum of squares, because we just summarized all of our squareds. Step number 5, we want to divide by n minus 1. to get us the variance. And then finally, because this is still squared deviations, we want to take the square root. All right, so the square root of variance is going to give us the standard deviation. All right, square root of s squared gives us s. Okay, so just a simple way. I know this took like what, an hour and a bit to get through this whole thing, but this is how it all works, right? This is the formula broken down. In fact, that's a good point. We should have so if we have the full equation, full formula for standard deviation, it's the square root of the sum of deviations squared divided by n minus 1. So this formula translates into this. We need the mean to find all those deviations, calculate all those deviations, then we square them all. Once they're all squared, add them together. Once we've got all of them added together, divide by n minus 1, and then finally take the square root of the whole thing. And that is standard deviation. And that is a very tough concept in statistics. So if you are struggling, that's fine. We're going to revisit this concept over and over. So again, just really wanting to emphasize the concept. What does the standard deviation tell us? Well, it tells us sort of on average how spread out are our data around the mean. What's the average distance of our data points from the mean? All right, if we have a very small standard deviation, that means the data points are really, really close to the mean. If we have a very big standard deviation, that tells us that the data points are more spread out from the mean. They're spread far away from the mean. Okay, so it tells us on average how spread out are our data around that mean.